Any questions? Okay. We last left off. I'm not necessarily going to do everything in sequence, but this chapter 2 is important enough that I will sort of pick up where we left off. All right, so I think this was one of the last things we did. I don't know if this is the same numbers or not, but I have these two forces that are pushing on a box. And so the question is, what's the total force?
2 newtons.
Positive 2 newtons.
Ooh. What have you forgotten if you say positive 2 newtons?
All right.
Yeah. At some point you need to define what positive is. So 2 newtons to the right, so we could just say positive, and so the total force, 2 newtons. Or you can put a plus sign in there if you just want to emphasize. All right, all that's well and good. We've got, I think, simple enough, even if you were thinking the answer was 8, which it's not. But let's make it look more complicated. Oh, questions before I make it look more complicated? Let's make it look more complicated. I have a box here. I'm pushing on it with 5 newtons that way and 3 newtons that way. Now, what is the total force?
-2? -2?
What would negative tell us?
Let's go to the left. We define positive as right.
If the positive, if to the right is positive, then
Negative would mean that it's going to the left.
yeah, except what do you do about that 3 there? That 3 is not going left or right. It's not that simple.
It wouldn't be positive 3 upwards, would it?
But just positive 3 up?
Positive 3 newtons up.
No. You're halfway there.
5 newtons to the right and 3 newtons up.
Yeah, there we go.
Join.
I had J hat.
Pardon?
I had J hat.
And ultimately, that's where we would head. So the longer version of it is you got that one, but you left this one off. It is 5 newtons to the right plus 3 newtons up. Or, because that's so much writing, let's simplify that. I'm going to say to the right, I'm just going to use I hat to represent to the right, and up, I'm going to represent as J hat. So I would just, so instead of writing out to the right, I'm just going to write 5 newtons I hat plus 3 newtons J hat. There we go. Now I've got a page 3. Yellow.
Ah.
Nope. Cancel.
believe I know how to.
Well, it's not giving me the graph screen anymore. Okay, that's not what I want. Ah, it just, yeah, God. The one across the way I can draw with my finger. All right. Now, this is just this is the simplest way of doing the sum of those two forces. This is known as rectangular notation because basically, if you, rectangles, you've got things that are perpendicular to each other. So rectangular notation. The other form is polar notation, of which we can deal with it conceptually and sort of sketch it out. There is a lab, which we probably won't do, where you need to get a protractor and graph paper and, you know, are very precise with it. But the other form of it is you're expressing, it's a vector, so you're expressing the magnitude and the direction. So polar form, I had to pick those numbers, didn't I? I'm gonna change that. No, I'll just call it a different problem. So if I have 4 newtons to the right and 3 newtons up, and I establish I hat is to the right, J hat is up, just so that I don't have to write out the words. In rectangular form, the force is 4 newtons I hat plus 3 newtons J hat. In polar form, and I'll sort of explain how I get here, but I'm just going to put down it's 5 newtons and about 37 degrees. This is polar form. Now, if you haven't had trig, getting that angle is really tricky, but trig is beyond the scope of this course, so I'm not expecting you to be able to get that angle, but I will, as I said, sketch it out. Questions before I talk about how we get 5 newtons or 37 degrees? Who in here has had trig? Some trig? Right triangle trig. Okay.
I've not had a trig class specifically. I've done things with trig, not a trig specific class.
Okay, that's probably good enough for this.
No, okay.
All right. So before we get to that, let's talk about adding vectors graphically. Now the textbook gets into a method that they call the parallelogram method, and I'm not a fan of that one. Parallelogram method is fine if I've got just 2 vectors that I'm adding together. It would work fine here. But if I'm adding more than 2, parallelogram method really becomes much more difficult. So when you're doing the graphic version of it, the length of the arrow is an indication of what the size is. So in this case over here, if I was drawing these arrows to do it graphically, this would be 5 something long, like 5 inches long, and that would be 3 inches long, or 5 centimeters, 3 centimeters, depending on what scale I use. This is 67% longer than that is. This is a third longer than that is. So when you're drawing it graphically, these lines would represent, the length of the line represents how much force there is if these are force vectors. So that's a longer line, represents a greater force than that does. The direction is indicated by how you actually draw the arrow. And when you add them, actually, let's go ahead and make that one longer. So when you add them, you start with one of them. It really doesn't matter which one you start with. So I'm going to pick one. I'm going to start right there, and I'm going to draw this one right here. Doing some incredibly sophisticated measuring. that vector and that vector are supposed to be the same length and the same direction. They should be parallel to each other and the same length. As long as they have the same length, same direction, they're considered equal vectors. So this is my starting point. SP for starting point. Now I'm here and I draw the second vector. And that's my endpoint. Now I haven't actually given an answer yet. All I've done is just basically drawn them together. The scalar analog of this is if I ask you what's 1 plus 2 and you said, well, 1 plus 2 equals 1 plus 2. That's all we've done at this point. The answer is a vector from where you started to where you ended. Let's see. That is the sum. It's basically as the crow flies, in a sense. This sum right here is known as the resultant. That's an R there. And this is the one place where I do the double print for the vector symbol. So pink is the result. The pink vector is my resultant. Let's just do another one of those. Let's see how well green shows up. Oh, that's not too bad. I have 3 vectors here, all starting at the same point, and I want to add them together. What is the sum of these 3 vectors? So I start with one of them. Again, it does not matter which one I start with. I'm going to start with this one. And I'm going to, so I take that. And apparently decided to do something different there. Those are supposed to be in the same direction and the same length. Now I'm here, so I draw the next one. And again, it doesn't matter which one I pick, just so long as it's not the one I just did. So if this is vector A and B and C, I started with vector A plus B. Again, connect the head from one to the tail to the other. This is why this technique is called the head to tail method. And then I take the last one. Around there. So again, I just set it up. I haven't actually written the answer yet, but now it's time to write the answer. It's from where I started to where I ended. That's my result. All right, questions to here? Ty?
And so is the idea that we would do this method on a graph and then make it into like a right triangle to find the resultant? Or
If you were doing it, there's several approaches. So in terms of what I'm trying to accomplish right now is to give you sort of another way of looking at the sum of these things, because I'm heading towards how do we get 5 newtons? How do we get 37 degrees? In terms of practical point of view, the advantage of this is if I give you a problem where I tell you I've got a force at, I got a 5 Newton force at a 37 degree angle, and another force acts at 4 newtons at a 120-degree angle, what's the total force? That you could somewhat sketch it out and have some general idea of what the answer is. So that's ultimately the intent of doing the graphic. Did I answer your question?
I believe so.
Okay. Well, as it evolves, ask again. Other questions?
So so when you're starting off, it doesn't matter which one you pick to start off the shape.
Right. Correct. Just like, officially, the commutative property of addition holds. Just 1 plus 2 is the same as 2 plus 1.
So hypothetically, if you were to have like 20 of those, doing this method would take a while, but it would still work?
Oh, yes. Yes, it would. Now, the disadvantage of this, if you're doing 20 of them, if you're adding 20 vectors together, is that on each one, if you're just a little bit off, that little bit off could potentially make you way off at the end. On the master set, there's a problem with 5 vectors, and get close. I mean, I can look at it and go, yeah, this person knows what he or she's talking about, or no, this person really does not know what he or she's talking about. So get close on a problem like that. Unless we do the lab, in which case, yeah, get incredibly precise. The disadvantage, the thing I like about the lab is that it should get really good results, which is not true for any lab you do. And the downside is it is a pain to grade. Probably a pain for the students to do too.
This is giving me, I forget the name of it, the compass. You go with the compass and you go 7 paces that way, and then you turn this to face this heading, and then you go another 9 paces that way.
Yeah, that pretty much adding vectors.
Yeah, that's just the kind of the idea that I was getting. But the point of it with the compass was, I was just trying to understand conceptually the point of it there, but then you would find that. Okay, I get it.
Yeah, so I did the context here of, I call these forces. It works for any vector addition that we're doing. So if instead of these are 2 forces acting on an object, suppose this was a person who was walking from, they were in a big field and they walked that way in a big field and then they walked that way in a big field. Where are they relative to where they started? Well, they ended up there relative to where they started. We could tack on some numbers with it. So if this is, let's just say that's represents 5 meters, that's less than 2 of them, so that looks like that's about 8 meters. It's a very crude rule of thumb here that we're doing. And my answer, well, let's see, that's 5. That looks like it's about 9 meters. If we wanted actual results, we'd have a ruler out, a scale. All right. So, where do we get 5 newtons from? Well, we're just adding them. I got 4 and 3 here. I went to the right 4 newtons. I go up 3 newtons. My resultant is from where I started to where I ended. If I drew it precisely, then I could measure that and figure out how long that is. Or, we do have another alternative. This 4 newton and 3 newton are a right angle. That's a right angle there. How would you find the hypotenuse of a right triangle?
A squared plus B squared is equal to C squared.
Yep, that's the one. Pythagorean theorem. Now, based on previous classes, most people are familiar with the Pythagorean theorem. If you are not, let me know, subtle nod. I'm assuming everyone has at least seen it before. All right, if you're sending me psychic waves, I'm not catching them. So 4 squared plus 3 squared is equal to c squared. That's 16 plus 9. 25 is equal to c squared, and so c would be 5. Was there a problem?
No, now I see where you're getting the 37 from.
Ah. If I drew this precisely, I could then take a protractor and I could actually measure that angle. Or, and this is a 30-second aside, if I spend more than 30 seconds on it, somebody stop me. We call this some angle theta. I have the opposite and the adjacent, SOHCAHTOA. I don't know if that's gonna ring a bell with, all right, I got a couple extra nods there. The tangent of this angle is equal to the opposite over the adjacent. So theta is the arctan of, that's 0.75. On most of your calculators, that would be tan -1 of 0.75. If you have no idea what I'm talking about here, don't worry about it. This was just an aside for those for whom it would help. This is beyond the scope.
Can you show us how you got 37?
Right there. If you do, you put into your calculator inverse tan or arctan of 0.75, 3/4 is 0.75. It should come out with 36 point something degrees.
Trig things, it's a whole thing.
3, 4, 5 triangles show up a lot in physics classes just because, well, it's a Pythagorean triplet, and you know, at this point, at some point, you know it's a 37-degree angle there, and the other one's 53 degrees.